Hello, everybody. This is our team's presentation of the energy infrastructure improvements for the Orica community on Isla Grande. This is a collaboration between students from Uni Norte and Penn State, as you can see there.
Orica is a community of about 1,200 people on Isla Grande with a warm climate and surrounded by the Caribbean Sea. And it's close to Cartagena, from where they import a lot of the things that they need. The community is remote, off-grid, and dependent on imported fuel and water-basic survival. Our project has four core goals. One is provide reliable clean energy, then ensure access to safe drinking water, keep the solutions economically affordable, and minimize the environmental impact, which matters because the island sits inside a national natural park. Then on the constraints, there's no grid connection, everything arrives by sea, and there is no utility data, no meters, no billing records, so all demand figures had to be estimated from standards and statements from the community and government.
To overview our design methodology, first we started with a baseline assessment to assess the stakeholder needs, their existing consumption of resources like energy, water, and fuel, and then to analyze other constraints. We then moved on to the energy technology analysis, which included estimating energy loads and evaluating potential renewable technologies and defining alternative scenarios to use as solutions. And then we moved on to modeling with Homer Pro, comparing our results and selecting the final design. And then eventually we did additional analysis of that final design, such as environmental, economic, feasibility, sensitivity, and reliability.
Isla Grande is an off-grid island community in Colombia, meaning it's not connected to the national electricity grid. Before this project, the community depended entirely on small diesel generators for electricity, with power typically available only for a few hours at night due to the high fuel cost. The island consumed more than 3,000 gallons of diesel per month, creating high energy costs dependent on fuel transport from Cartagena and environmental impact within a protected marine ecosystem. Because there is no formal system to track electricity consumption, the community's energy demand has to be estimated using diesel consumption data and information from similar off-grid communities.
So to overview our energy load cases, we decided to break our analysis into 6 sections. The section 1 was the baseline case, and then for the additional load cases, we added in new elements of energy loads for the community. So one of those components was the expected increase in demand when we produce more electricity. We also considered the increase in electricity demand for electrifying cooking and water production with desalination. We considered adding air conditioning capacity as a service to the community, which increased the energy load a lot. And then we also considered reduction technologies such as solar hot water, which reduced the total energy load.
The first technology that we explored was solar photovoltaic system integrated with battery energy storage. This alternative was selected after performing the Homer Pro optimization across multiple system configurations and load cases. The PV battery offers flexible integration, compatibility with the storage technologies, and compliance with the Colombian law for renewable energy system. The photovoltaic system consists of 4,332 panels rated at 450 watts each, and for energy storage, the design incorporates 3,528 batteries, ensuring reliable operation during periods of low solar irradiance and improving the overall system stability.
For desalination, you can see your key design assumptions. We're designing the whole minimum standard of 20 liters per person per day, which give us a capacity of 20 cubic meters per day for the community. In the center, we compare 7 desalination technologies. As you can see, we choose seawater reverse osmosis. That is the only mature member technology that handles full seawater salinity. The salinity, we're working with our 42% recovery rate. And finally, the system requires 39 megawatts per year for producing up to 6,000 cubic meters of clean water.
So the wind technology was considered within this work due to the adequate geographical proximity to the ocean of the island and the consistent existing winds. Also, this model of 30 kilowatt wind turbine was considered due to the flexibility of sizing and installation. As there's a no-gear component wind turbine, and also accounts for creating these hydraulic tower facilities that adequate installation and compliance with local laws. So for the Homer per modeling, the general process that was followed was to convert the energy per month estimates to an average power demand value, and also to consider different for the chosen technologies, the energy demand on the material cost, installation, and maintenance costs, and along with the availability of the possibility to be able to purchase these technologies to be installed and considered for the community island. And all this was considered modeled within Homer Pro, adapting a Homer optimizer, the Homer optimization feature to be able to size the number of converter and panels. Finally, for the cost analysis, the scenarios where solar hardware was involved represented a lower levels energy cost, capital expenditure, and net percentage cost. Therefore, the analysis was done through these technologies. And finally, the use of solar hardware eliminated the use of importing LPG or water to the island, which is part of the objectives of the project. Therefore, the case 4 is one that was considered for final.
So the final proposed system is designed as a fully off-grid solar microgrid capable of supplying renewable electricity to the entire community using only renewable energy. The system is mainly composed of 4 parts: a solar photovoltaic array that generates electricity during the day, a battery storage system that stores excess energy for the nighttime use and when there are cloudy periods, a protection and power distribution subsystem, and a group of inverter chargers that convert and regulate the electricity supplied to homes and community facilities. During daytime operation, the solar panels supply electricity directly to the community while also charging the battery bank. When solar production decreases at night or during low irradiance conditions, the battery provides backup energy to maintain continuous service. The design also includes solar hot water, desalination, and electricity cooking system in order to reduce dependence on imported fuels and improve overall living conditions with the community.
One of the main factors of this project is environmental sustainability. Our baseline assessment reveals that the community currently consumes over 11,000 liters of diesel per month, which translates to approximately 300,000 kilograms of CO2 emissions every year. By implementing our proposed configuration, we can achieve a 100% renewable energy fraction. This reduces Scope 1 emissions to 0 kilograms of CO2 per year. Additionally, by producing water and energy on site, we eliminate the carbon footprint associated with the maritime supply chain currently required to transport water and LPG from Cartagena to Isla Grande. The selected system includes solar panels, a battery bank, and solar water heaters, which together can meet the community energy needs in a reliable way. The economic benefits are very clear. The cost of energy is reduced by about 82% compared to diesel. With an initial investment of around $3.6 million, the system recovered its cost in less than 2 years when compared to continuing with diesel generation. In addition to providing electricity, the system also supplies 20 cubic meters of safe drinking water each day and supports the community cooking needs, eliminating the need to import LPG and water from Cartagena. Finally, we conducted a sensitivity analysis to assess the project's performance under different conditions. The results show that the project is most sensitive to changes in diesel prices. As diesel costs rise, the system becomes significantly more attractive and generates higher savings. Higher discount rates reduce the net cost but increases the levelized cost of energy, although the project remains competitive in all its scenarios. At the same time, lower solar capital costs improve feasibility and shorten the payback period, while stable solar irradiation keeps resource risk low. In addition, increases in water and LPG costs further strengthen the project's value, and reducing dependence on imports improves reliability. Overall, the project remains financially and operationally robust, even under conservative assumptions.
The system operates across 3 distinct modes. During daylight hours, the PV array supplies the community load directly and simultaneously charges the battery bank. During the transition periods, generation, sunset, and sunrise, the generation and storage share the load during nighttime hours. The battery bank supplies the entire community demand. To preserve the battery lifespan, the depth of discharge is recommended not to exceed 30%, setting a minimum at 20, yielding a practical operational autonomy to approximately 26 hours. The integrated solar hot water system additionally offset 10% of the electrical demand independently, reducing daily cycling pressure on the storage bank. Regarding the maintenance, the system is designed for a 25-year project life. The photovoltaic modules require cleaning due to the salt from the coastal environment, and the battery bank is expected to require full replacement every 5 to 7 years, representing 3 to 4 replacement cycles over the project. And the inverter bank is anticipated to require a single replacement year 12. In summary, the system is operationally straightforward and fully renewable, but its long-term reliability depends on the disciplined battery management and the structured replacement planning across its 25-year design life. These are our reference, and thank you very much.